Hey everyone, welcome back to another thrilling, exciting, wonderful discussion of matter and heat. Okay, so this is lecture number 21, and I'm going to do a lot of hand waving, a lot of talking, and a lot of words. No math, so hopefully you'll like this part. Okay? All right, let's look what we're going to talk about. We're going to talk about the kinetic theory of matter. Very simple words. I'm going to tell you what temperature means to a scientist, to a physicist, or a chemist. And we're going to discuss some methods of heat conduction, of heat transfer, and then we're going to discuss change of phase. And those are just a bunch of definitions I'm going to require you to memorize. Okay, first, kinetic theory of matter. All right, when we write the gas laws, Charles' law, Boyle's law, the law of Gay-Lussac, it turns out there's a bunch of assumptions that go into this. As we'll see later when we talk about chemistry, we're going to be dealing with so many particles, 10 to the 23rd, what's called Avogadro's number of particles, that we have to make approximations, we have to use statistics, and life gets really complicated. But there's a couple of assumptions in the kinetic theory of matter. So let's just look at these, okay? Just to be complete, so you have an idea. Let's suppose we have a container. What container? This room is a container. And inside this room are molecules of air. Okay? What is air mostly made of? Do you know? You should know this. It's approximately 78% nitrogen and approximately 21% oxygen, N2 and O2. 1% methane and all the other stuff, carbon dioxide, etc. All right, so suppose we have a room or we have a box or we have a container and it's got gas particles in it or molecules. Okay, it doesn't matter, atoms, it doesn't matter, whatever the particles are. The first assumption of the kinetic theory of matter is that particles do not interact. Okay, kind of like people, they just walk by and they don't interact. Okay, the second assumption is that when particles do collide or they do hit each other, they don't lose any kinetic energy. When particles collide, no loss of kinetic energy. We say that's an elastic collision. Now, when two objects in real life collide, for example, if two cars collide outside your window, do you know about it? And the answer is yes. How do you know? Because sound energy, kinetic energy is lost as heat and sound and bending the bumpers, so energy is lost. Here we're assuming particles. Here's a particle, zipping. There's a particle, zipping. There's a particle, zipping. They're all just moving their own way. If they do collide, if this guy collides with another guy, they just bounce off. They don't make a sound because that would be losing energy. They just bounce off with no loss of energy. And the third assumption in the kinetic theory of matter is that the particles are tiny, minuscule compared to this separation. Okay, here I drew them as circles. I could draw them as little dots. Okay, little dots moving. Okay, so there's my dots. The size of the dots are tiny compared to the separation of the particles. So these are the assumptions that go into the kinetic theory of gases. Okay, I'm going to keep this picture here. I'm going to erase the assumptions and discuss for a second the idea of temperature. When something's hot, what does it mean, temperature? What does temperature mean? Now, when I discuss temperature, everything I say is going to be on the Kelvin scale. Another name for the Kelvin scale is the absolute scale. Why is it absolute? What about the Celsius scale and the Fahrenheit scale? Well, if you remember, the Celsius scale is an artificial scale. It's human made. It's based on, does everybody know what it's based on? It's based on the boiling and freezing points of water, 0 to 100. And the same for the Fahrenheit scale, based on the boiling point, 212, and the freezing point, 32 of water. The absolute scale has nothing to do with water. So all calculations are always done on the Kelvin scale. All right, let's talk for 1 second. Earlier in this chapter, matter and heat, we talked about heat as energy. And earlier than this, we also spoke about conservation laws. Remember what a conservation law is? Conservation law simply states that what you start with is equal to what you finish with. Simple. So we mentioned conservation of energy. The total energy you start with equals the total energy you finish with. We spoke about conservation of momentum, linear or angular. The total momentum you begin with has to equal the total momentum you finish with. So we're going to talk about temperature, and we're going to talk about conservation for a second, okay? So I want you to watch, just watch. No math, just concepts, okay? Suppose this was a square balloon, okay? Suppose I put here some heat energy, okay? Those are my arrows, and those are my sound effects. So heat energy, right? We usually call it heat Q. Again, I don't care if it's calories, I don't care joule, I don't care what units, just some heat. I'm going to heat up a balloon, or I'm going to heat up a system. If you add heat energy to something, then the energy must go somewhere. Okay? That's conservation of energy. Now, where does the energy go? Well, these particles are zipping around. Each particle in this system has a kinetic energy. Remember, kinetic energy is 1/2 mv squared. What is v? It's the speed or velocity. If I add heat to a system, one thing that can happen, and does happen, is the particles get extra energy, get more kinetic energy. What does that mean? It means they move faster. We also know what else happens. When you heat something up, what happens? It's a silly question, and you're going to say, oh, it's a trick question. It's not a trick question. When you heat something up, what happens to a system? The answer is the temperature goes up. Now, I'm telling you, if you heat something up, the heat energy has to go somewhere. Where does it go? It makes the particles move faster. The particles move faster, and the temperature increases. They're related. So I'm going to tell you what temperature is. Temperature on the absolute or Kelvin scale is a measure of the, look at this word, average kinetic energy of the particles of the system. So that's a definition of kinetic energy, of temperature. It's a measure of the average kinetic energy. Now let's talk. Room temperature, what is room temperature? Room temperature is about, say, 300 Kelvin, 300 Kelvin. So let's look. This eraser, this marker, is at 300 Kelvin. It's room temperature. This eraser is at 300 Kelvin. They're made of different things. What does this say? If they're at the same temperature, what that means is the particles in this eraser are wiggling, moving, have a kinetic energy, the same kinetic energy as the particles in this marker. The same kinetic energy as the particles in this book, on this the paper molecules. They're all moving at the same average kinetic energy. Why? Because they all have the same temperature. If I had a bottle of water, I do have a bottle of water, isn't that? Here's a bottle of water. It's at room temperature. How fast are these water molecules moving? Well, they're moving at exactly the same speed as the molecules in this marker, as the molecules in this eraser, as the molecules on the desk, as the molecules on this board. If you're at the same temperature, Kelvin, then you have the same average kinetic energy. Okay? One more point I want to make about this. If you heat this up, and you know this happens with a balloon without breaking it, if you heat things up, these molecules, now think of molecules or atoms moving around. I think of them as like little bees moving, and they're hitting the walls of the container. If you heat something up and now these particles move faster, then they're hitting the wall harder and harder and harder of the balloon. What does that do to the balloon? It makes it expand. If you increase the kinetic energy of a system, the particles move faster. If they move faster, think, boom, no sound. They hit each other and they whack and go farther apart. What that does is if there's containers, it pushes more on the containers, increases the pressure. And also what it does is it increases, besides the kinetic energy, it does some work if it moves, if the container is allowed to move. Remember, if you, work is force times distance. If you move the walls, you're doing some work. So adding heat can do some work, okay? Can make the thing move. Right? This is actually a statement of the first law of thermodynamics. Okay? It's also called, for the chemist, the law of Clausius. You know who it's named after? Ah, very good. Clausius, chemist. And what the first law says is exactly what I said in words. It says this. It says, if I add heat energy to a system, where does that energy go? Well, it can increase the kinetic energy of the particle, or the particles in the system, and or it can do work. It can move the walls. So the first law of thermodynamics is a fancy or a thermodynamic way of talking about conservation of energy. Okay? So the first law of thermodynamics is just a restatement of conservation of energy in a thermodynamic sense. So in other words, if I add heat energy to a system, the heat energy has to go somewhere, has to be accounted for, right? Energy you start with has to equal the energy you finish with. It's accounted for by making the particles move faster. Some of the energy goes there, and some of the energy goes into doing work if you can move the walls. Remember, conservation of energy for the diver problem. She has all potential energy, right? Her total energy is all potential. As she falls, as she dives, her potential energy decreases, her kinetic energy increases, but her potential plus her kinetic must be the same, must equal the initial total energy. All right, so the first law of thermodynamics, the law of Clausius, is merely a statement of conservation of energy. If you add heat energy to something, the kinetic energy can increase and you can do work. All right? So temperature on the Kelvin scale is a measure of the average kinetic energy. Now, there's a second law of thermodynamics, the law of entropy. I'll do that in the next lecture because I really want to give that time and talk about it because it's kind of interesting in words. So we'll discuss the second law, the law of entropy, in the next lecture. But for now, let's finish off this chapter. We mentioned the kinetic theory of matter. I just told you that temperature is a measure of the average kinetic energy of a system. So if you're at 300 degrees Kelvin, 300 Kelvin, then your particles are moving with a certain kinetic energy. Everything at 300 Kelvin has the same kinetic energy. Does that mean the particles in this marker have the same speed as the particles in this eraser? They're at the same kinetic energy because they're the same temperature, room temperature. Does that mean the particles are moving, wiggling at the same rate? The answer is no. They have the same kinetic energy, but remember, kinetic energy is mass times v squared, 1/2 mv squared. So some particles could be heavier than the others, so the speed could be different, but they could still have the same kinetic energy. All right? All right, what I'd like to talk about now quickly, briefly, is heat transfer. And there's 3 ways of transferring heat. Only 2 we will discuss in this chapter. So there's 3 ways of transferring heat: conduction, convection, and radiation. We'll do radiation later. We're going to talk a lot about radiation. First, I want to talk about conduction, heat conduction. Okay, Heat conduction comes about by direct contact. All right? Now, before I mention this, before I talk about this, I want to tell you a law. And it's really interesting. When people ask, why does that system do this? Why does this happen? Why does it? In nature, in physics, in chemistry, in biology, almost always the answer to a why does a system do that, is this. I want you to learn this, memorize this, remember this. Everything wants to be in its lowest energy state. Every system wants to be in its lowest energy state. And so if I have a system at a very high energy state and I put it in contact with a system in a very low energy state, what happens is they reach an equilibrium where the entire system is at the same energy state. The high energy state goes down, the low energy state comes up, and they meet a nice medium. So that's essentially what heat conduction is, all right? Suppose you take a hot frying pan. What do I mean by hot? Well, you just took it off the stove. It's really hot. What does hot mean? Hot means it has a high temperature. What does that mean? High temperature, remember, high temperature means the particles in that frying pan, copper, aluminum, whatever it is, those particles are wiggling very fast. What do I mean wiggling? They have a very high kinetic energy. So I take this frying pan with particles moving really fast inside the pan. Now I take it and I put it in cold water. Now cold water or room temperature water, those molecules in the water are moving, they're wiggling at whatever kinetic energy is room temperature, they're wiggling. Now I'm taking particles from a pan that are wiggling like this. They're going to hit water molecules that are moving like this. And what happens is eventually they all move at the same rate. If they all wiggle or move at the same rate, means they have the same average kinetic energy. If they have the same average kinetic energy, that just means they're at the same temperature. But you know this. You know when you take a hot frying pan, put it in the water, the frying pan cools off and the water heats up and they reach an equilibrium. So, heat conduction is direct contact. Okay, the heat conducts, and that means the particles all eventually touch each other and start wiggling at the same rate. They all have the same kinetic energy. All right, second thing, heat convection. Heat convection kind of combines a couple of ideas, something I just said. When you heat a system, remember when I heated the system, the molecules move faster, means when they hit, they spread apart. So let's talk about density for a second. Imagine we have 30 people in a room, 30 people. So the density is 30 people in that volume, right? That's my density. If I take the same number of people, 30 people, and put them in an Olympic stadium, I have 30 people in a very large volume. The number of particles, the number of people is the same, 30. But now the volume has increased. So what is the density? The density decreases. Okay? So if you heat something up and the volume increases, the density of that system decreases. Why? Same number of particles in a greater volume. Okay? So heat convection, an example of heat convection is a fireplace. I also want to tell you that all of our weather comes from heat convection. What do I mean? Okay, let's look. The second thing that comes in has to do with Archimedes' principle about density and why things float. But let's look for a second. Here's my fireplace. Hot air. Okay, so this has heat, Q. And as it heats the air, what happens is hot air is less dense than cool air. Right? Why is it less dense? Because the particles push apart. Same number of particles in a bigger volume. So what happens is, again, by Archimedes' principle, since they're lighter, just like a cork would float on water or ice floats, the hot air rises. Hot air rises. Why? We just said it, less dense, right? It floats in the cooler air. So what happens is, as the hot air rises, the cool air fills its place. And so what you end up with is hot air rising, cool air coming down. And this is convection currents. And again, if we look at the Earth, and we look at our beautiful star, the sun, what it's doing is it's heating the ground, right? Hot air goes up and cool air goes down. And so all of our weather patterns have to do with this circulation of heat convection currents. Okay? As I mentioned, radiation, a third way of transferring heat, we'll talk about later in another chapter. All right, finally, for this lecture, because again, next lecture I want to discuss the second law of thermodynamics dealing with entropy, but that's a separate lecture. But here I want to talk about change of phase. Okay? What are the phases of matter? Well, you should know this. What is S? Is solid. L is going to be liquid. And G is going to be a gas. Okay? Remember, liquids and gases are both fluids. Don't forget that. Okay, solid, liquid, gas. Change of phase, and you just need to, I'm not going to go into it, you're going to learn these phrases. If you take a gas to a liquid, right, what we call that is evaporation. When a liquid goes down to a gas, the opposite reaction is condensation. When a solid heats up and melts, goes to a liquid, we call that melting. When a solid goes to a gas, solid directly to a gas, skips the liquid phase, this is called sublimation. So I'm going to write here solid to gas, sublimation. An example is dry ice. What's dry ice made of? Carbon dioxide. So it's solid carbon dioxide, goes directly to a gas. Another example is a mothball. I don't know if you've ever smelled mothballs. They're kind of small, right? Mothballs also go from a solid directly to a gas, right? That's called sublimation. And when a gas goes directly down to a solid, that's called deposition. So you should learn these phrases and hope that silly thing like that, nice definition, is on an exam. All right? In the next lecture, as I said, we're going to discuss the second law of thermodynamics, entropy. Once again, no math, just a discussion, and I'll throw in a little philosophy for you. All right, have a great one. Be safe. Peace.